So we are in the process of beginning to learn about taking our knowledge of linear motion and applying it to rotational motion. Because objects that are round, they both translate like a golf ball, and they move along in the x direction, but they also roll. They rotate around an axis. And it's the combination of these two motions that we want to understand, because we may face a question, more likely a conceptual question about these motions than an actual calculation question. But rotational kinetic energy, we've seen 1/2 mv squared. If you want to take an object and you want to get it from rest to a certain velocity, 1/2 the mass times the velocity you're looking for squared gives you the amount of work you must do to get the object moving at v. So that's the kinetic energy. Rotationally, we have only to substitute the variables we've learned about. Instead of m, we use I. So we use the moment of inertia, which is how the mass is distributed around the axis of rotation. The further the mass is from the axis of rotation, the larger the rotary mass or moment of inertia. And instead of v, we have omega. And we know that linear guy is going to be rotational guy times r. So omega times r is v, the relationship that we have between rotational variables and linear variables. So now a round or rolling object has two pieces to it. It has these two energies. So a rolling disc, and that's the side, it's like a coin, a disc, and it rolls along. Some of the energy is 1/2 mv squared, and some of the energy is 1/2 I omega squared. So let's factor out what's common to those, and or substitute. We have 1/2 mv squared, and in linear terms, 1/2, and the I, or moment of inertia for a disk, is 1/2 mr squared, where r is the radius. And the omega is v over r, because v is omega r. Linear guy is rotational guy times r. So divide by r, and we'll get omega v over r, and it's squared. So if I simplify this, I have r squared on top and r squared on the bottom. They cancel. And I have 1/2 of 1/2, which is 1/4, mv squared plus another half. 1/2 and 1/4 is 3/4 mv squared. That is the total energy, some of which is in rotational form, some of which is in translational form. But that is the total energy of the disk. Now, if you thought to ask, is it always 50-50, half of it's rotation and half of it is translation, that'd be a nice guess. I mean, I give you credit for thinking about that. If the thought occurred to you how much is in each one, good for you. In this particular case, 1/3 of the kinetic energy is rotational and 2/3 of it is linear. How do I know that? Because the moment of inertia is some constant mr squared. Remember when we were going over the different objects, and we said that for a mass on a string, it's 1 mr squared. For a disk, it's 1/2 mr squared. For a bar of length L, it's 1/12 ml squared. For a sphere, it was 2/3 mr squared. If it was hollow, if it was solid, it was 2/5 mr squared. The further away the mass is from the center of rotation, the bigger I is. So here in this case, the kinetic energy, or in any case, it'd be 1/2 mv squared plus 1/2 some constant that I call beta, the second letter of the Greek alphabet, mr squared, times omega squared. And remember, since v is equal to omega r, omega is always v over r, and I've substituted that in here. And I have brought these factored out 1/2 mv squared, and I've got the r squareds canceled, and I get 1 plus beta. So that, and I ask what fraction of this is linear? If this is the total amount, what fraction is the 1/2 mr squared? Well, that would be 1/2 mr squared, or mv squared rather, the linear amount, times the total amount, 1/2 mv squared 1 plus beta. And those cancel. So 1 over 1 plus beta is the amount that is stored in linear. And for a disk, beta is 1/2. 1 plus 1/2 is 3/2. So 2/3 is in linear, because beta is 1/2. For a disk, it's different for every object. And therefore, what's ever left, 1 minus this, which is beta over 1 plus beta, add them together, 1 plus beta over 1 plus beta, you get 1, or 100% of the energy. 1 over 1 plus beta is the fraction that's in the linear domain for energy, and beta over 1 plus beta is the fraction of energy in the rotational frame. So now I have a way of getting these numbers easily with beta. What would it be for a sphere? Well, for a sphere that's solid, beta is 2/5. So 1 over 1 plus 2/5 would be 1 over 7/5. 5/7 of the energy would be locked in linear, and 2/7 would be locked in rotational. So we're always able to say what part of the energy is rotational, what part of the energy is translational. The sum of them is the total energy of the object. And that's going to help us as we begin to formulate a way of talking about the full motion of an object that can both rotate and can translate.